Okay, triangle similarity. So specifically, we're talking about a theorem called the angle-angle similarity theorem. A couple of topics. We're going to talk about triangle rigidity, the angle-angle-angle similarity theorem, the fact that we have a shortcut to that, and I'll run through some examples. Okay, so this is called triangle rigidity. It's not really important for you to remember this. The thing for you to remember is this right down here. Triangles are special. It comes from the fact that there's a way of explaining this mathematically, but I like this visual here. If we take a couple of, let's say, hinged pieces of wood, and we take them and we make a triangle, if you push on one of those corners, if they're all attached, the triangle's not really going to change shape. It might bend a little bit, but it would spring back into its original shape. If you did that with a square, if you pushed on one of those corners, then the whole thing would kind of flop into a rhombus instead of staying as a square. So this makes triangles special, and all other polygons would do what the square did, and it would kind of compress and change shape. But the triangles are special, and other shapes that kind of have triangles within them can tend to be special too. So what this means is that when we talk about similar triangles, we're going to get to take a couple of shortcuts. Because if you remember, similar figures have two criteria. We have to have corresponding angles are congruent, and the corresponding sides are in proportion. So here's an example of two similar triangles. All of the sides are in the same proportions, we have a scale factor of 2, and all of the angles are congruent. Since triangles are special, though, we can actually prove that two triangles are similar with only knowing that we have the 3 pairs of congruent angles. So all of these triangles that you see here, even though we don't know the side lengths, we do know that they are similar. This goes back to the fact that triangles are special. Doesn't work for other polygons. This only works for triangles. Don't be fooled into thinking that you can just check angles with other polygons. You need to continue to check the ratios of the sides. Okay, so because of the triangle sum theorem, which we did in class, the 3 angles add up to 180 in a triangle. If you know 2, you can find the third. So in this little simple problem here, we have 88, we have 35. So if we add up 88, 35, we get 123, and we subtract from 180, we're going to get 57. I shouldn't even need to do the math in the smaller triangle or this other triangle because it should be 57 again. So if I know 2 angles are congruent, I'm automatically going to know the third are congruent because I'm going to find the third angle the same way. Even in a situation like we have over here on the right, even if I don't know what those angles are, so I'm not told the measurements, but I know that angle C and angle Z are going to be congruent because the other 2 angles were congruent as well. So whatever these 2 angles here and here are, I'm going to subtract them from 180 to find C. And I'm going to do the same thing over here, but these were the same numbers as they were on this side. So when I subtract these 2 from 180, I'm going to get the same answer for Z as I did for C. So this means that triangles have an even further shortcut. So if we just need to show that 3 pairs of angles are congruent, you really only need to show that 2 pairs of angles are congruent. So, are these 2 triangles congruent? Well, let's take a look at the angles. Here we have 30, we have 102, that's 132, which means our last angle over here is 48. I don't even need to find angle M because I have 2 pairs of congruent triangles. So, triangle EFG is similar, 1 squiggle, to triangle, and I want to try to name them as the same way, EFG. So I want to do L, M would be corresponding to F, and then N at the end. Are these 2 triangles congruent? If so, write a similarity statement. All right, well, we have 1 angle, back up. We have 1 pair of angles already congruent, here, and we have vertical angles that are congruent. So yes, we have angle-angle similarity. So triangle ABE, so I started with this angle, I'm going to start over here, is similar to triangle CDE. One last quick example, and then I'll show you a couple that aren't similar. This one, we have a parallel line. Never forget your parallel line stuff. So we have corresponding angles here and here, corresponding angles here and here. So we have two pairs of congruent angles, and actually we have the third. H is congruent to itself. So triangle HLI is similar to triangle HKJ. So here's a couple of non-examples. If you see here, 81 plus 60 would give us 141, so then we would have 39 left. And so if I put 39 degrees here, that's not going to match two angles with the other triangle, so not similar. And then over here, we would figure out that this is going to be 105, and 105 plus 55 will get us up to 160. So that would mean that this angle up here is 20 degrees. So we don't have, in this triangle, we don't have two pairs of congruent angles. So those two are not similar. All right, don't forget to summarize. And yes, this should look familiar because we've already done similar figures. We're just doing them specifically with triangles now.